All right, in this screencast, I want to play with a couple of ideas that we do with teenagers, but we can't justify with teenagers, and that's a little bit annoying for me as somebody who likes to lay things out, and somebody who likes to lay things out in a very sequential way. Let's remember what we're dealing with here. That's one. This is the graph of 1 over x. And we always talk about E as the number for which this area, the integral from 1 to E of 1 over x dx, is 1. We talk about E as the number that makes this area equal to 1. Having area equal to 1 is valuable. I do tell teenagers about that. I draw the picture. I say E is really important for this reason and for other reasons that will become clear as you study. Now, you and I both know why we love E so much. E is the number for which the derivative of the exponential function is itself, right? That's what we really, really love. Like we can do derivatives of other exponential functions, but we have to multiply by the natural log of the base. And if the base is E, then that natural log is 1. So that's really clean. But that's not something we can talk about with teenagers without making up some hokey thing where we graph y equals e to the x, and we say it's really, really important for us that the line that ever so gently kisses this curve right at x equals 0 has a slope of 1. How do we know that? Well, we sort of do, and that's kind of a mystery also, how that gets laying out there. What's more crazy is that we talk about this thing. We talk about how the limit as h approaches 0 of 1 plus h to the 1 over h is, by some people's version, a definition of E. This is the thing where if you really, really wanted to go down this road, this is the deal where you invest $1 at 100% interest, and it's compounded every moment for a year, and you get E dollars. And so when you start doing the algebra 2 stuff with interest, if you really want to take this to the nth degree, so you would say, hey, let's take $1, let's invest it at 100% interest, which is totally ridiculous, and let's compound it every moment of every minute of every hour of every day, which is also totally ridiculous, for a year, and you get somehow this magic E dollars. But why is that even true? Well, it's true because we know what the derivative of the natural log function is at x equals 1. We know that this is the limit as h approaches 0 of the natural log of 1 plus h minus the natural log of 1 over h. And we know what the natural log of 1 is because we defined it. So this is the limit as, fraction bars! Limit as h approaches 0 of 1 over h times the natural log of 1 plus h, right? And this 1 over h can become a power because that's a natural log. So this is the limit as h approaches 0 of the natural log of 1 plus h to the 1 over h. And we know what the derivative of the log function is at 1. That's 1. And if the natural log goes to 1, then the thing itself goes to E. So with teenagers, you have to make up a ridiculous example and use your calculator and get 2.718281828459045. But in calculus land, that falls out really, really nicely. Okay, so logs and exponents are intricately linked. When we do natural log functions as inverses of exponential functions, that's on purpose. The fact that logs are in proofs of things involving E see that that does make perfect sense. Uh, Logs and exponents play together very nicely throughout Algebra 2, throughout pre-calc, throughout Calc 1 and 2, and beyond. And that's probably sufficient for us to talk about here. Hope that these screencasts were helpful to you as you were processing what you read in your book, and I'll see you when we gather in class.